Hi, my name is Janne. This video presents fractional marginal pseudo-likelihood, which is a method for learning Gaussian graphical models. This method can be applied even in high-dimensional settings. It requires no hyperparameters to be tuned, and it's not restricted to chordal graphs like many of the Bayesian methods. We will start with a quick recap on the basics. Gaussian graphical model has essentially two components: a random vector x following a multivariate normal distribution and an undirected graph G that specifies the conditional independent statements between the components of x. Now our task is to identify the undirected graph G based on the observed data x. Using a Bayesian approach, we will score the graphs by their posterior probabilities. The data-dependent term in the posterior probability is the marginal likelihood, which is hard to compute in the general case. We use pseudo-likelihood in place of the true likelihood in order to factor the marginal likelihood integral over variables. We have terms where each variable xj is conditioned on its Markov blanket, denoted by mbj. This integral is connected to a marginal likelihood of a Gaussian directed acyclic model. Each variable's Markov blanket corresponds to its parents in a DAG. Making use of the previous results concerning the objective comparison of Gaussian DAGs, we obtain the fractional marginal pseudo-likelihood. Reference priors and fractional Bayes factors are utilized in order to derive the original formula. Our scoring function has several attractive properties. It factorizes variable-wise and is consistent so that we can find each node's neighbors independently of each other. In practice, we optimize each node's neighbors using greedy hill climbing. However, since consistency is an asymptotic result, the found neighborhoods are not necessarily consistent with each other. We use two heuristic criteria to produce proper graphs. This example shows how the learned Markov blankets are transformed into a proper undirected graphs. Here we can see that 2 is neighbor of node 1 and 1 is a neighbor of node 2. So this edge will be present in the AND graph. No other edges are present because, for example, 2 is not a neighbor of 3. However, these all edges appear in the OR graph. The next example shows the methods in action. The true data generating graph is shown in the center of the picture. Methods and OR try to learn the graph using different sample sizes.